Thanks, so it's going to be a tutorial on two-round finality. As you just heard, it's been a sort of quite a hot topic recently, I guess in part because of Solana's transition. Oh, I didn't turn the mic on, sorry. Okay, so as I was saying, this has been quite a hot topic recently, in part because of Solana's transition to Alpenglow, but there are also a number of other protocols out there. So the aim is today you should come away understanding like a couple of very simple approaches to achieving two-round finality. Okay. So first of all, though, I better explain what two-round finality is. Okay, so throughout the talk today, we're talking about protocols for state machine replication. Okay, so this is basically, I presume everyone's familiar with SMR. So this is just what blockchain protocols have to do, right? So just informally speaking for now, so we have a set of users or clients, what do you want to call them? And then a set of, so sometimes they're called validators, sometimes I'm going to call them processors, okay? So the users are submitting transactions to the processors, and the processors then have to sort the transactions into a sequence or log, if you like. So each processor maintains their own version of this log. Okay, and may require consistency, so correct processors don't disagree on the ordering of transactions, and liveness, so all submitted transactions get added to the log. Okay, so I think everyone's familiar with this anyway, right? And a bit of terminology that I'll be using the whole time. So when a processor adds a transaction, TR, say, to their log, we say it finalizes that transaction. Okay, so throughout this talk, we're going to consider a fixed set of N processors, P up to Pn, and there's this known bound F, right? So we know that at most F processors can be faulty. And throughout this talk, we're going to imagine Byzantine faults. That just means that processors, the faulty processors can behave arbitrarily. Okay, we're going to be focusing on the partially synchronous model of message delivery. So again, I think everyone's familiar with that. It doesn't really matter that much if you aren't completely familiar, because I'll remind you of the sort of more precise definition in a bit. But for now, basically the partially synchronous model just means that messages can take arbitrarily long to be delivered, but are also guaranteed intervals in which message delivery is reliable. Okay, so messages are delivered within a known bound delta. So in practice, what that means is you have to design protocols that satisfy consistency no matter how long messages take to arrive, and then you can use the sort of synchronous intervals to achieve liveness. Okay, so now we get to the actual definition. Well, again, I'm going to start off informally, right? So informally, what do we mean by two-round finality? So generally, SMR protocols are divided, have instructions that are divided into sort of views or rounds, right? You have view 1, then view 2, and so on. Each view or round generally has a different leader. You've got a leader for the view 1, then a leader for view 2, and so on. The two-round finality means that if the leader is correct, and if we're in synchrony, then the view basically progresses as follows, right? So the leader will propose a block B. So that's round 1, that's your first round of communication. And then other processors will vote on that block. Okay, that's round 2, that's your second round of communication. Okay, and here we just have a single round of voting. Okay, so now the block is finalized. I'm receiving a single quorum of votes. I'm getting sufficient many votes from that single round of voting. Okay, so maybe it's slightly confusing. So two-round finality means one round of voting. Three-round finality means 2 rounds of voting. And generally, R-round finality means R minus 1 rounds of voting. Okay, so it's worth pointing out at this point, again, as I assume people are probably aware, so standard protocols, sort of like PBFT, 10-to-mint simplex, etc., they all assume that less than a third of the processors are faulty, and they have 3 rounds of finality, 3-round finality, so 2 rounds of voting. So the assumption that less than a third of processors there, that's less than a third of the processors are faulty, that's optimal, right? If you're working in partial synchrony, you need to make that assumption, no matter how many rounds of voting you have. Okay, but actually, you can then, if you have that assumption, you can achieve 3-round finality. So the obvious question then is 2-round finality even possible? And actually, we've known for some time that it is, right? So actually, 2-round finality is possible so long as we're prepared to make stronger assumptions on the size of the adversary, the number of faulty processors. Okay, so particularly, so if n is greater than 5f plus 1, then you can do it, and actually it's possible even only if n is greater than 5f minus 1. Okay, so today I'm not going to worry that much about the plus and minus 1 there. Okay, strictly it's 5f minus 1, but normally protocols with 2-round finality assume n equals 5f plus 1, or n is greater or equal to 5f plus 1. Yeah, so I said there's been sort of a lot of focus very recently, maybe in part because of Alpenglow. There are also a number of other recent protocols, Kudzu, Hydrangea, Minimit, and others. So what we're going to do today, so first of all, I'm going to go through what I think is probably the simplest protocol. I guess these things are a matter of taste, but I think probably Minimit is the sort of, to my mind anyway, the simplest version of a protocol with two-round finality. Okay, so this is a protocol in the sort of simplex style. So everybody's now familiar with simplex because Itai's talked yesterday. Okay, so it's in the same sort of style. So yeah, that's the first thing we'll do. And okay, sorry, so Minimit, I mentioned various other protocols there. Kudzu and Alpenglow are sort of similar, and then a similar sort of style to Minimit. On the other hand, there are other approaches. So the Hydrangea is another recent protocol. And it has a sort of alternative approach to view changes. It's more sort of PBFT style approach. Okay, so I'll also describe an alternative approach along those lines. It won't actually be Hydrangea, maybe a sort of simplified protocol. And then if there's time at the end, I'll talk a bit about how to integrate erasure coding with two-round finality. Okay, so let's start off. I'm just going to explain Minimit. I'm going to explain it in complete detail, but so it's a simple protocol, I promise. But maybe you have to sort of focus a bit to get all the details. Okay, so let's go. Okay, so to remind us of the setup, we've got n processors. Okay, P0 to Pn, and we're supposing now that n is greater or equal to 5f plus 1. Okay, we're imagining faulty processors can behave arbitrarily here. Okay, we're working, as I said, in partial synchrony. Okay, I gave you a sort of informal description before, so a precise definition, which I think everyone is probably familiar with. Again, this was certainly mentioned in the talks yesterday. So a message sent at time t arrives by time max t and GST plus delta. So basically there's this known bound delta, there's some unknown time GST, and message delivery is reliable after GST. Messages always arrive in time delta after GST. And then, okay, some more terminology, which I'm sure people know, but just to make sure. Okay, so we're going to consider a protocol that produces blocks of transactions. So each block will contain like a sequence of transactions. Each block has a unique parent. Okay, the ancestors of a block B are B and all ancestors of its parent. So in particular, I'm going to assume B is one of its own ancestors. Okay. Everybody starts off by knowing this unique genesis block, and every block has to have this genesis block as an ancestor. Okay, so for any block, you should be able to, here's block B, here's your ancestors that you trace back to the genesis block. Okay, and we'll say B prime is a descendant of B if B is an ancestor of B prime. Okay, so for each block, you've got its ancestor going back to genesis, then it may have a whole bunch of descendants. Okay, so here's the intuition then. Okay, so we're going to divide the instructions into views. Right, view 1, view 2, and so on. Each view has a leader. For now, for the sake, it doesn't really matter, but for the sake of being concrete, let's suppose that the leader is just rotating. So P1 is the leader of view 1, P2 is the leader of view 2, okay, and so on. Obviously, once you get up to Pn, you just rotate back to the beginning. Okay, in each view, okay, the leader is going to propose a block, right? So I'll form a block, and I'll send it to everybody else. And there's going to be a single round of voting. Okay, now, in sort of standard protocols, a quorum or a QC, like a quorum certificate, is a set of n minus f votes. Right, that's what we're used to. We require n minus f because we can't expect the F40 guys to send in votes. Now we're going to consider two different types of quorums of different sizes. Okay, and I'll explain why in a bit. Right? So an LQC, where L stands for large, okay, so that's still a set of n minus f votes. But now we're working with the assumption n is equal to 5f plus 1. So rather than being sort of like 2/3 of the votes, this is now you can think of this as being sort of 80% of the votes. Yeah. Okay, so that's an LQC. And then an MQC is a smaller set of votes. And here you can think of the M as standing for mini. Okay. So an MQC is a set of 2f plus 1 votes, a smaller set of votes. Okay, you might immediately wonder why you're considering these different sizes, but we'll come to that in a little bit. Okay, so first of all, let's just think about how the protocol behaves like under standard operation. Right? So when the leader is correct and we're in synchrony. Okay, so here it's extremely simple. Okay, so the leader proposes a block B. I was supposed to delete that, but then okay, the leader will just propose a block B. All the other processors will vote for B. Okay, and obviously we have to come to later on exactly how does the leader propose B, when will other processors vote for it, and so on. But we'll fill in those details. Okay, then That's basically all that happens, almost. So then you just proceed to the next view on receiving the MQC, and you finalize on receiving the LQC, the larger quorum. Okay, so if you think of the sequence here, normally all the different processes will be different parts around the world. So you'll get the smaller quorum first, right? You get the smaller quorum first, and then a little bit after that, maybe you get the larger quorum. Okay, so in standard operation, that's all that happens, right? It's the leader proposes a block, people vote on it, you proceed to the next view on getting the smaller QC, the MQC, and then you finalize on getting the LQC, and that's it. Okay, so details we have to fill in here, as I say. So we have to explain, okay, how does the leader determine which block to propose? When will other processes vote for it? But I guess the immediate question in your mind is, okay, so why proceed on receiving the MQC, the smaller QC, and why should the MQC be 2f plus 1 votes? Okay, so let's explain that first of all. So the basic point here is this. So, okay, so correct processes, right, they're going to vote at most once in each view. Okay, so that immediately means the following. So an LQC precludes an MQC for other blocks. Okay, so if a block B for view V receives an LQC, then no other block for the view receives an MQC. And why is that? That's just your standard sort of counting argument applied to this setting. Okay, so it's your standard sort of quorum intersection argument, right? Okay, so towards a contradiction, suppose otherwise. Suppose processes in P vote for B, okay, and at least n minus f processes vote for that then, so it's got the LQC. Suppose processes in P prime vote for this other block B prime, okay, and it gets the MQC, so it's getting at least 2f plus 1 votes. Then you just look at the size of the intersection, right? It's the standard form of argument. Size of the intersection is at least the n minus f plus 2f plus 1 minus n. So the intersection is at size at least f plus 1. Okay, so it has to contain a correct processor. Okay, but that means some correct processor votes for both B and B prime, and correct processors don't do that, so that's contradiction. Okay, so this is our basic fact, right? So an LQC precludes an MQC for other blocks. Or to spin that around, that means an MQC for B proves that no same view block, different block B prime, receives an LQC. Yeah. Okay, if B's got an MQC, no other block can get an LQC in that view. Okay, so now suppose PI is the leader of the next view, view V plus 1. Okay, so PI receives an MQC for B, like in view V. If they send that to all others, then okay, everybody has proof that no block other than B could have been finalized in view V. Yeah. So PI can propose a block with B as a parent. Everyone knows it's safe to vote for PI's proposal. Okay, that's the sort of basic thinking behind these MQCs. We'll see an actual proof of consistency later, right? Okay, so this is claim 1, right? Okay, so I want you to, yeah.
So just sort of looking ahead, should I think of every block will eventually get an LQC, or could you be finalized just kind of more because someone after you get?
Yeah, so it's always going to be the case if one of your descendants gets an LQC, then you necessarily have an MQC, and you could be finalized that way. Yeah. Okay. Okay, so so this is claim 1. I want you to remember this fact. Claim 1: LQC precludes MQC for the blocks. Okay, just a simple counting argument. Okay, so far we've considered what happens when things go right. It's very simple, right? Leader proposes, everyone votes, proceed to next view on MQC, finalize upon LQC. Okay, so what happens though? So far processes only proceed to next view on getting an MQC. So you've got to worry what happens if none is produced, right? In other words, like for example, if you have a faulty leader, we need to ensure progression through views here, right? So what do? We just do the obvious sort of thing you'll have seen many times. Well, you've seen it from Simplex. So upon entering the view, processors set a timer. If the timer expires before they vote, so I put the information 2 delta there. Don't worry about the fact that it's exactly 2 delta for now. I'll explain why it's 2 delta later. For now, just imagine it's some sort of appropriate length of time, right? So if the timer expires before they vote, processors send a nullify message, and then will not vote. Okay, so if they vote, then they're not going to nullify. But if they don't vote, and the timer gets to that point, so it seems like things aren't going well, then they'll send a nullify V message, and then they won't vote. Okay, and you can think of the nullify V message as indicating they want to move to the next view due to a lack of progress in view V. Okay, and then you proceed to the next view on getting 2f+1 nullify v messages. Okay, I'm going to call this, a set of this kind, I'm going to call it a nullification. So it's kind of annoying. I've been using slightly different terminology, so I think this was a skip certificate yesterday. Okay, so I'm calling it a nullification. Okay, so you can set a timer. If you don't vote on time, you send a nullify v message. Everyone's going to proceed to the next view, we're getting 2f+1 nullify v messages. We call that a nullification. Okay, so then we'll come back in a little bit to whether this suffices for view progression. For now, though, I want you to note the following fact, which is kind of analogous to claim 1. Okay, so remember, claim 1 was an LQC precludes an MQC for other blocks. Okay, here's an analogous claim. So since correct processes either nullify or vote, right, according to the instructions we just wrote, they either nullify or vote, we have an LQC precludes a nullification for the same view. So if a block B for view V receives an LQC, then the view V does not receive nullification. And why is that? That's just exactly the same argument, basically, right? So proof is the same for claim 1. So the quorum intersection argument for claim 1 used that correct processes don't vote for two different blocks. Now we just carry out the same argument using the fact that correct processes don't vote and nullify. Right, so if you like towards a contradiction, imagine otherwise, let P be the processes who contribute to the LQC, that's of size n minus f. Let P prime be the processes who contribute to the nullification. Look at the intersection. You've got some correct processor must nullify and vote. Yeah? So it's exactly the same argument. Okay, so the LQC precludes nullification. So to spin that around then, a nullification for view V proves that no view V block receives an LQC. Okay, so I'm going to call that claim 2. Okay, so claim 1, LQC precludes MQC for other blocks. Claim 2, LQC precludes a nullification for that view. Everyone happy so far? Okay, so now we've added in a couple of other extra instructions, right? So let's see our full protocol so far. Okay, so here are the instructions for view V. Okay, so on entering the view, you set your timer to expire in 2 delta. We'll explain the 2 delta in a bit. And if you're leader, you propose a block. Okay, upon receiving a first valid proposal, before the timer expires, you vote for that proposal. That's one possibility. Other possibility, if that doesn't happen, if the timer expires before voting, then you send a nullify V message. Okay, so the leader proposes, either you vote or you nullify. And then you enter the next view on receiving either an MQC for some view V block or a nullification for the view. Okay, and so there are 2 different ways we live in the view there. Right, if you receive an MQC for view V block, right, that proves no other block for the view receives an LQC. If you receive a nullification for the view, that proves that no view V block receives an LQC. Okay, so that's almost the whole protocol. Obviously, we have some details still to make more precise. Okay, so we still to specify. So when the leader proposes a block, how do they do that? Right, how do they choose a parent to build on? And when will other people vote for their proposal? When will they consider it a valid proposal? Okay, so let's do that next. And the good news here is that, yeah.
So just to clarify, so you could have multiple mini quorum certificates
Yeah.
in the same view. Right?
Yeah.
And so I guess when you propose, you have to decide arbitrarily which
Yeah.
one is then.
Yeah. Well, I guess you're proceeding on the first one you see, so you'll yeah. Okay. Mm-hmm. There's a question behind you, Tim.
So question is it the nullification message necessary? I mean, is the nullification message to be excluded or removed?
Well, certainly in this protocol, they're playing a vital role. I'll talk about another approach later on, which is more in sort of PDFT style. It doesn't use nullifications. So there are other approaches, but I mean, yeah.
This gets me about the size is fixed, the size of the stack is fixed.
The size of the
stack, the size of the stack is size is fixed.
So the number of processes, yeah.
And in this case, so is it possible to just remove this message?
No, well, certainly in this part protocol, it's playing it. The nullification is kind of evidence that another block hasn't been nullified in the view. It's going to be a very crucial part of the logic, you'll see. Okay. I mean, it's playing the same role here as it does in simplex. Okay, so that's basically the protocol, but we've got some details to sort of fill in. How do you propose a block? And when do people vote for a block? But the good news here is this is basically essentially exactly the same as for simplex, which you saw yesterday, right? So everyone knows this. Okay, so suppose Pi is the leader of view V. What do they do? Well, on entering the view V, Pi finds the greatest V prime less than V, such that it's received an MQC for some block B prime for view V prime, right? And it proposes a block with B prime as parent. Okay, so you look at the greatest V prime less than V, such you've got an MQC for view V prime. And you use that corresponding block as the parent. Notice here that since Pi has entered view V, it's received nullifications for all the views in the interim, right? Because to leave a view, you've got to receive an MQC or a nullification. Okay, so it's got to have had nullifications for all views in the interim. Okay. And we're going to imagine here that people as soon as you first receive an MQC or nullification, you send it out to everybody. Okay, so if you get it, everyone else is going to get it pretty quickly. Okay, so that's how leaders propose. It's basically the same as for simplex, but we're using MQCs. And then others will vote for B as long as they see an MQC for the parent B prime and nullifications for all views in between V and V prime. Okay. And like I said, right, so since all processes, including Pi, resend MQCs and nullifications on first receipt, so if the view V begins after GST, then Pi can be sure, right, all the processes will receive the messages they need to vote for the block. Right, they'll get the MQC for the parent, they'll get nullifications for all views in the interim, so they'll be able to vote for the block. So that already means, right, we basically liveness is going to be fine, right, so long as we can ensure progression through views, right. As long as we can ensure progression through views, each leader is going to be able to, they'll propose a block, everyone will vote for it. We have to check the timeout works, but liveness will be fine as long as we can ensure progression through views. It's also easy to see that consistency will be satisfied. So let's see that proof now. Okay, so towards a contradiction, suppose some block B1 for view V1 receives the LQC. Okay, so it's finalized in that view. And then there's a least view V2 greater than V1, such that some block B2 for V2 that does not have B1 as an ancestor receives an MQC. Okay, we're going to have a consistency violation. This will have to occur. Well, immediately from claim 1, right, so LQC precludes MQCs for other blocks in the same view. We know V2 is greater than V1. But by our choice of V2 as the least such view greater than V1, right, and since correct processors won't vote for blocks until they see an MQC for the parent, okay, that means the parent of B2 must be for a view less than V1. Because if V2 is greater than V1, the parent's for a view less than V1. Okay, but this immediately gives us a contradiction, right? Because correct processors will not vote for B2 and view V2 without they need to see nullifications for all the interim views, right? So they need to see a nullification for view V1. And we know such a nullification can't exist by claim 2. That was precisely claim 2. We've got an LQC in that B's got the LQC. So that precludes a nullification for that view. Okay, so where are we? So we've got consistency is fine, and hopefully agree quite simple. We've got liveness is going to be fine as long as we can ensure progression through views. Okay. So now let's come to that, and we will have to add in one extra instruction. Okay, so the problem here, maybe the view produces no MQC or nullification. Right, so for example, the leader might be annoying, they might send out lots of different blocks to different people, so they're all voting, okay, but no single block gets an MQC. Okay, so what we're going to do now, so to ensure progression through views, we are going to sometimes allow processes to nullify after voting, but we're going to do it so as to maintain claim 2. So if you remember for claim 2, that was LQC precludes nullification. Part of the argument was that you don't nullify and vote, right? You do one or the other. But now we're going to drop that. We're going to say, okay, sometimes after you've voted, we're going to allow you to nullify, but we're only going to do that in such a way that claim 2 will still hold. It won't harm our claim 2. So what do we do? Okay, so now correct PI is going to send a nullify V message under the following conditions. Okay, so first of all, Condition A is just the previous condition. So if their timer expires before voting, then they'll nullify. That's the same as before. And now we've got to add in a second condition, right? And what we need, fairly clearly, is what we need some condition that doesn't spoil claim 2, right? And which will definitely be satisfied if the view doesn't produce an MQC or a nullification. Okay, so it's actually going to solve our problem for us.
So remind me, so what does the leader, a Byzantine leader, do to make sure, so that there's no MQC or nullification?
What is a Byzantine? Oh, he could just send, yeah. What? Yeah. So the leader could, for example, just send like a different block to everybody. Each person gets a different block. Then everyone votes, but you don't get any block with an MQC, for example. Yeah. Okay.
If there's no evocation, it's fine?
I guess it would be, yeah. If the leader only sends one block, it would be fine. Yeah. Okay, so we need some condition on these lines. So here I'll just tell you the condition, and then we'll see that it works, okay? Okay, so the condition is the following. Well, so you're going to send this nullify v message if you receive messages from 2f+1 processors, each of which is either a nullify v message or a vote for a view v block different than a view v block that PI has already voted for. Okay, 2f+1 messages, each one either a nullify v message or a vote for a block different than one you've already voted for. Now, the immediate observation here is that this can't violate claim 2, because if a view v block receives an LQC, then B will never be triggered, right? We'll never get to this point. This is just, again, it's the same quorum intersection argument, right? If you've got an LQC, look at the processes you've contributed to that, look at the set of messages this size, and then look at the size of the intersection. Yeah, it's just not possible. Okay, so B will never be triggered in the case that we get an LQC. So there's no problem in violating claim 2. Remains to show the second condition, right? We also want B to be triggered if the view doesn't produce an MQC or nullification. So let's see that then, okay? So here I've just put the B condition up to the top of the screen. Okay, so now suppose the view produces no MQC or nullification. Well then, what do we know? We know each correct processor will eventually receive from at least n-f processors either a vote or some vote for some view v block or a nullify v message. Because each processor, if they don't vote, they will eventually nullify, right? So you're going to get at least one of these from everybody. Okay, so if PI is correct and votes for some view v block B, let's say, then let's do the counting. So if the view doesn't produce an MQC, then it can't get 2f+1 votes for its own block, right? So it receives at least n-f in total minus 2f potential votes for its own block. That's n minus 3f, which is greater than or equal to 2f+1, because we're assuming n is greater or equal to 5f+1. Okay, it receives at least 2f+1 messages, each either a nullify v message or a vote for a view v block other than the block it's voted for. Okay, so we just simple counting argument. Okay, so that means PI sends a nullify v message via clause B. Okay, so every processor then produces a nullify v message, and that gives us our contradiction. Okay, so we have view progression, just with this extra little clause here, B. Okay, so that's the full protocol then. So let's just review the protocol. So we've seen it satisfies consistency, liveness, as long as we have view progression, and now we have view progression as well. So we've got everything we want, okay? So the instructions for review as follows. So on entering the view, you set your timer to expire in 2 delta. Okay, so now we can see why 2 delta. So everyone resends MQCs and nullifications on first receipt. So that basically means after GST, everyone's going to be entering views within delta, time delta of each other. Yeah? So if you think of the first processor enters a view at time t, the leader will enter by t plus delta, they'll immediately propose, and everyone will receive their proposal by t plus 2 delta. Okay, so we can set our timer to be 2 delta. Okay, so on entering the view, you set your timer to 2 delta, and propose a block of leader. Okay, I'm receiving a first valid proposal before your timer expires, you vote for it. On the other hand, if your timer expires before voting, you send a nullify v message. That's where we were before. And now we can add in this extra condition, right? So you also send a nullify v message upon proof of no LQC for view v. Okay, that's our new instruction. Okay, I stated that at a fairly high level, but I gave you a precise form of that on the previous slide. Okay, then you enter the next view. I'm receiving either an MQC or a nullification. Okay, so that's the whole protocol. Mm-hmm. we need a mic, so maybe I can push you.
Well, so you kind of assume a reliable broadcast,
There's no assumption of reliable broadcast.
but you are rebroadcasting.
Yeah, you just send to everybody. So the only assumption is, if you send someone a message after GST, they'll get it in time delta.
Yeah.
So people could, a Byzantine person could send that to some people, not others. There's no.
Yeah, but this is like a gossip communication of that dimension, right? There's a gossip communication property of that dimension.
We're not using a gossip technology. We're just imagining that there's a private channel between the clerics.
Yeah.
The standard setup.
This communication step is not counted in the two, right? The communication step of rebroadcasting your own.
Yeah, we're counting that as a communication step. You allow time delta for it. It's just standard. So think about the view, for example, like if the first process to enter view does so at time t, the leader will enter by t plus delta. All the MQCs notifications they've sent, you imagine that for that point that they will then everyone receive them by t plus 2 delta.
Communication delays with communication steps.
I don't get what you mean. Sorry. Maybe explain to me afterwards. But yeah, okay. So that's the full protocol. Everybody happy with that? Yeah.
Yeah, I mean,
No, you need a mic. Okay. I may have to switch it on. I think I'm not sure.
yeah, just to comment that this is there's a trade-off here, right? So by sending kind of a notification later, you delay the worst case view. So what you could have done is like basically take these n-f messages and think about them as kind of notification certificates, and that would only happen if there's a kind of a equivocation, like going back to you. So I guess you can kind of save a round by sending a larger
You were
message.
saying you could rather than sort of send another IV message, you could rebroadcast the message that caused you to send it. Or like that.
If you show the whole n-f messages that show that there is no MQ, but there is a...
Yeah, I guess you're probably
That's
going to
kind of
still
true,
need to
right?
resend some of those messages to make sure everyone else is
So
seeing
that's a
them.
certificate, right? So
Yeah.
that message is a certificate. So you can either start it, if you care about
Yeah.
that, or you can just send that as a large certificate.
Yeah.
Now it's a large message, sure, but it only happens if there's an equivocation.
Yeah.
So if there's like a slashing event, you're throwing them off, like your validator is now like
Yeah.
completely missing.
So you're saying there are some situations.
It
that
might
cause
be
you to send
worthwhile to actually do it.
Mhm.
You both like do it, save it around, right? And sure, you're sending a larger message, but this only happens if you're kind of under attack, under kind of business.
So in this scenario, we're sending out an extra nullified IV message. You're saying send a certificate instead in that case?
The n-f message that you see
Yeah.
is a certificate.
Yeah.
It's essentially a nullification certificate. of the certificate. It's a proof of nullification.
I'm not sure it's going to save it, but okay. Big good.
Yeah,
So I'm not
yeah,
sure that was
analyze
saving
latency.
anything on the time. Anyway.
If you analyze the worst case latency, right,
Mhm.
then this will give you like, this protocol is like 2 delta plus 2 delta.
You mean so that the length of view is 2 delta? And you're saying the worst case length of view.
Yes, yes.
Okay. I mean, I'll need to talk through that. Okay. Okay. So Minimit is as one protocol. There are other protocols. So basically, I went through Minimit because I think it's probably the sort of simplest possible protocol, and so I didn't sort of emphasize it there. But so an advantage of Minimit is it allows for fast view progression, right? So you're progressing to the next view and getting 2f plus 1 votes. For other protocols, the sort of standard is, I mean, you haven't seen them yet, but I'm telling you, for other protocols, the standard is you progress on getting 3f plus 1 votes. So normally that takes slightly more time. So Minimit allows for some faster view progression, and so that actually reduces latency slightly because it means that you're waiting less time to be included in a block. And for fixed size blocks, that's going to increase throughput as well. So yeah, there are a number of other protocols. I'm not going to sort of talk in detail about like Kudzu, Hydrangea, Alpengo, etc. You already heard about Alpengo, but just at a high level to point out some of the differences. So Kudzu is another sort of recent protocol. So one difference with Kudzu is that they have this sort of sliding parameter p. Okay, so rather than considering n is greater or equal to 5f plus 1, you assume n is 3f plus 2p plus 1. Okay, you can tolerate f failures. Okay, and you have fast finality if less than or equal to p of 40. So if you want to think just about comparing apples to apples there, you can just put p equal f, and then it's basically the same thing. Okay, but there's just another sliding parameter you can play with there. So could you add a slow path? Okay, but the slow path, if you're comparing to apples, doesn't change your resilience. Okay, any increases resilience as P is less than F. Then alpenglow you heard about yesterday. Okay, so alpenglow assumes n equals 5f plus 1. There's also some increased resilience to benign faults, but not under your standard assumption of partial sig free. Okay. Then hydrangea, I should have said just to emphasize, so kudzu and alpenglow, these are both simplex style protocols. Okay. The reason I think, yes, all these things are a matter of taste. I'd say minimit is slightly sort of simpler. Basically, because with the other protocols, the requirement for 3f plus 1 votes before view progression sort of slightly complicates the mechanism for ensuring view progression. Okay, so if you want a high level view of what their instructions look like, it's kind of similar to minimit, I'd say, but it's a bit more fiddly to ensure the view progression. Okay. Then hydrangea is really it's a bit different. So hydrangea also includes a slow path and actually has increased resilience to crash failures on the slow path. Okay, but without minimit's fast view progression. A difference with hydrangea is that it's not a simplex style protocol, right? So it's more in the sort of PBFT. It uses a PBFT style approach to view changes. So I'm not going to describe how hydrangea works. I'm just going to go through how you can achieve two-round finality using this sort of PBFT style approach to view changes. Okay. Yeah.
So in this kind of protocol, you have OS which is more quick, since you keyword OS more quickly, but you have less validation. For instance, if you OS more quickly, but you have to unify many votes and you have to get back in time. You really have a gain, or it's great. OS more slowly, but more assurance.
So it might be harder to finalize a block. Okay. The quorum for finalizing blocks is the same, right? So it's the same in it's always n minus f. So that's not changed. It's just literally the conditions for view progression. I don't see how that's making anything worse.
Maybe my point of view is you maybe have attacker but try to make the progress in the wrong way. You actually more, since you switch view more quickly, you can have attacker that try to.
But I'd say that there's nothing weaker about the guarantee you're getting here upon that progression, that fast progression. You've still got the same guarantees, it's just mechanisms, and you can do it quicker. I don't think there's anything. If there's something you're losing, I don't know. Maybe there is. Okay, so yeah, so what we're going to do next is we're going to, where are we? 9:40, okay. So we're going to explain how to achieve two-round finality using a PBFT style approach. But first of all, we better explain how to achieve three-round finality using this approach. Basically, because at least the way I'm going to present it, the two-round finality approach is a sort of a slight complication of the three-round finality version. Okay, so now we're going to step back and now we're going to assume again that n is greater to 3f plus 1. Okay, and we're going to give a high-level description of a protocol that uses 2 rounds of voting again, okay, in each view, and which uses an approach similar to PBFT for view changes. So this would actually be PBFT, it just be sort of a protocol that I think is kind of as simple as possible, but using this approach to view changes. Okay, so consider a protocol with the following instructions for each view. Okay, so on entry, set a timer. Okay, I guess we're used to that. And propose a block of leader. And later on, obviously, we'll specify how leaders propose. Upon receiving a valid proposal before time expiry, you send a stage 1 vote. Okay, and obviously later on, we have to specify how validity is defined there. Okay, but so far, it's all just what you'd expect, right? Entire standard. And now that we've got 2 rounds of voting. Okay, so upon receiving a stage 1 QC, where stage 1 QC is n minus f stage 1 votes by different processors. Right, upon receiving a stage 1 QC before time expiry, then you send your stage 2 vote. Okay, so now we have our second round of voting. And blocks are now finalized upon receiving a stage 2 QC. Okay, so n minus f stage 2 votes. And just a little observation at this point that will be useful later on. Okay, so if a block B receives a stage 2 QC, well, you only send your stage 2 vote upon receiving a stage 1 QC for the block. Okay, so anybody sending in their stage 2 vote is sort of testifying to the idea that they've seen the stage 1 QC. So there are sort of n minus f processes doing that. Of course, f of them might be faulty. So you've got n minus 2f less. So if B receives a stage 2 QC, then at least n minus 2f correct processes see a stage 1 QC for B before timer expiring. Okay, that's just an observation along the way that will be useful later on. Okay, so far, leader proposes, stage 1 vote, stage 2 votes. Okay, and then, again, as not that surprising, so upon timer expiry, we're going to send a timeout message for view V. Okay, so we're going to specify the form of the timeout messages later. So these are kind of a bit like a nullify V message, but there's a difference here, right? Because we're not saying if you haven't voted or something, just upon timer expiry, you definitely send a timeout message. Okay. And a set of n minus f such messages we're going to call a timeout certificate, a TC for view V. Okay. You might wonder why I'm not using the word nullification again, but the TC is playing a different role than nullification, so I'm giving it a different name. Okay, and then you proceed to the next view and receive a stage 2 QC or a TC. Okay. As I said, so one sort of difference between this and the simplex style approaches, so now a TC for view V no longer precludes a finalized block during the view. Right, previously, it was kind of like, don't nullify if you've already voted. But now, whatever happens, once your timer expires, you're going to send this timeout message. And that basically, that's making view progression easier, right? Because you'll automatically get view progression. Basically, everybody eventually, if they're in the view long enough, they'll send this timeout message, and you'll get your TC, so you're going to proceed. Okay, so that's something that's kind of, in the mind at least, sort of simpler than, simplifies the approach, right? You definitely get view progression. Okay, so hopefully that form is clear, right? You enter, leader proposes, stage 1 votes, stage 2 votes. Once your timer expires, you're going to send a timeout message. And then you proceed to the next view on getting a stage 2 QC or a TC. Stage 2 QC is obviously evidence that the block has done well, right? We finalize a new block. Okay, so that's basically the protocol. But to specify the protocol fully, explain why it works, right? We're going to need to describe the form of timeout messages, how leaders propose, and the definition of a valid proposal. Yeah, and that will fit in. Then we'll have a complete description. Okay, so let's deal with the timeout messages first. Okay, so when PI sends a timeout message for view V, well, it does it so it finds Q, which is the greatest stage 1 QC it's received, ordered by view. Okay, you find the greatest stage 1 QC you've received. Then you send the message VQ, right, signed by PI. So V is the view you're leaving here, right, and Q is some QC, could be for a view less than V. And it's important that this is signed because then it could be used as evidence of what PI said was the greatest QC they'd seen when they left the view. Okay, so it's just a message saying this is the greatest QC I've seen upon leaving view V. Okay, so that's the timeout message. Now let's see how leaders propose blocks. So when entering view V plus 1, leader PI obviously has to select an appropriate parent, right? So first of all, there's a simple case, which is if the previous view has produced a QC, then you know what to do. Okay, so if it's received a stage 1 or stage 2 QC for some view V block, B prime, let's say, then it just uses B prime as the parent. It proposes a block with B prime as parent, and it includes that QC for B prime as what I'm going to call a justification for the proposal. Okay. Then on seeing the justification, others are going to regard the proposal as valid and will vote for it. Okay, you know, it was obviously, if it's got a QC, it was fine to vote for it in the previous view. Nothing's happened in between. There are no views in between, so now it's fine to use that as the parent. Yeah. Okay, so that's the simple case. On the other hand, okay, view progression is either by stage 2 QC or TC. So if that isn't the case, then PI must have received T, let's say, which is a TC for the previous view, right? Instead of n minus f timeout messages. So what does the leader do then? So then PI finds the maximum QC included in all those timeout messages in the TC. Okay. If that QC, let's say, is a QC for B prime, then PI proposes a block with B prime as parent and includes this TC in the block as a justification. Okay. So you can find the maximum QC included in the TC. If that QC is for B prime, you use B prime as the parent. Okay, then other processes regard the proposal as valid if basically the TC points to that parent, right? So if they look at the maximum QC included in the TC, and if that is a QC for the parent, then they can vote for the block, no matter what they've received, right? Just that justification itself means it's okay to vote for the block. Okay, so any questions about that?
So just the maximum is maximum view, right?
Maximum view, yeah. Okay, so now let's see why that works then, right? So suppose some block B1 for view V1 is finalized. Okay, and towards a contradiction, suppose there's some least V2 greater equal to V1, such as some block B2 for view V2 receives a stage 1 QC, but doesn't have B1 as an ancestor. Okay, so before we go for the full argument, so the rough argument here is just going to be as follows. So some correct processor must contribute to the stage 2 QC for B1 and the TC included justification in B2, just by your standard intersection argument, right? Okay, so some correct processor will contribute to the stage 2 QC for B1 and the TC includes justification. And that will give us an immediate contradiction. This is a contradiction because they must have seen the stage 1 QC for B1 before casting their stage 2 vote. Okay, so let's see that in more detail. Okay, so first of all, by the standard quorum intersection argument, we know V2 is greater than V1. Okay, you can't get QCs for different blocks in the same view. By our choice of V2, though, as the least such view, the parent of B2 must be for a view less than V1. Okay, and B2 must include T, which is a TC for the previous view as justification. Okay, well then the greatest QC in any message in T is for a view less than V1, because the parent's for a view less than V1, and people are voting for this block. And now we just do our counter argument. Okay, so let P be the processors who contribute to the stage 2 QC for B1. Note the correct processors in P see a stage 1 QC for B1 before leaving the view. That's the observation we made earlier on, right? You send your stage 2 vote upon seeing a stage 1 QC. Let P prime be the n minus f processors contributing to the TC. Okay, by the standard argument, the intersections of size at least f plus 1, so we have to include a correct processor. And this contradicts the 2 points we made above, right, 1 and 2. Correct processors in P see a QC for view V1 before leaving the view, but the greatest QC in T is for a view less than V1. Okay, so the sort of timing here is as follows. So here's view V1. Well, in view V1, some correct processor that's in the intersection must see a stage 1 QC for B1. But then, on entering view V2, when they're sending this timeout message, they report a QC for view greater to V1 when leaving that view. Okay, so the next thing I want to do is to take that idea and extend it a bit to 2-round finality. But maybe we can have a sort of 5-minute break then, yeah? Yep, so we'll do a 5-minute. Do people want a break? Yeah. Okay, we'll do a 5-minute break and then I'll come back. Okay, cool. Okay. Okay, so we've seen the PBFT style approach to view changes with 3-round finalities. Now let's apply the same thing to 2-round finality. Okay, so now we're returning to the setting where n is greater to 5f plus 1. I'm going to describe a protocol with 2-round finality. Okay, so recall, so an MQC is a set of 2f plus 1 votes, and LQC is the larger one, a set of n minus f votes. And recall also, so long as correct processors vote at most once in each view, an LQC for B precludes an MQC for other blocks in the same view. Okay, so let's first summarize the instructions for each view. Okay, so consider a protocol with the following instructions for view V. Okay, so on entry, you set a timer and propose a block if leader. Okay, and obviously we need to explain the exact process for proposing a block. On receiving a valid proposal for timer expiry, you send a vote. Okay, but again, obviously we're going to need to expand on that. What do we mean by a valid proposal? Upon timer expiry, you send a timeout message for view V. Again, this is unconditional. It's not if you haven't voted or something. Just upon timer expiry, you send your timeout message. And obviously we're going to need, again, to specify the form of the timeout messages. Okay, and then you proceed to the next view upon receiving an MQC or a TC. Yeah, everyone happy with that? Yeah, so your basic form. So On entry, set a timer, proposal block of VIDA. Upon receiving a first valid proposal before timer expires, send vote. Upon timer expiry, send a timeout message. Proceed to next view upon receipt of MQC or TC. And TC here is a set of N-F timeout messages. Okay, so to specify it fully, explain what it works, we need to describe the form of timeout messages, how leaders propose, and the definition of a valid proposal. Okay, so let's start out with the timeout messages. Okay, so when PI sends a timeout message for view V, it finds Q, which is the greatest MQC it's received, and V, which is the greatest vote it's sent, and it sends the message VQV, signed by PI now. So it's the same as before, but we're adding in a vote entry now. Okay, same thing, but we add in a vote. How about block proposals? Okay, so on entering view V+1, lead has to select an appropriate parent. So to do that, it does as follows. So first of all, there's the sort of simple case if the previous view has produced a QC. So if it receives an MQC for a view V block, take the latter block as parent, include the MQC as a justification for the proposal. Okay, that means it's fine to vote for this thing. On the other hand, okay, otherwise, PI, this leader, must have received T, which is a TC for view V. So what does PI do then? Well, first of all, it finds the maximum QC included in any of those timeout messages in the TC. Okay, suppose that QC is for block B1. And then it does an extra thing. That's what it did before. Now it does an extra thing. Now it finds the greatest block B2, if any, such that T contains an MQC for B2 amongst its votes. Yeah, an extra condition. And then we take, let B prime be the whichever of B1 and B2 is for the greatest view. Yeah. And we use that as a parent. Then you propose B with B prime as parent, and you include T as the justification. Right? And what do others do? And when do they consider it valid? Well, others will regard the proposal as valid if it includes a TC specifying B prime as a parent via this calculation above. So they just look at the TC, they do this calculation, and say, does it specify the parent that it's using? Yeah? And if so, they can just vote for it, right? Independent of what they received. Right? The justification itself should allow them to vote. Okay, so let's see why this approach works. Okay, so suppose some block B1 for view V1 receives an LQC. Then we know already no other block for view V1 receives an MQC. Okay. So towards a contradiction, suppose there's some least V2 greater than V1, such that a correct processor votes for B2 for view V2, and B2 does not have B1 as an ancestor. Okay, the rough argument now is going to be as follows. Okay, if you do this sort of core intersection argument now, we'll find that at least 2F plus 1 correct processors contribute to the LQC for B1 and the TC included in B2. Okay, so previously, normally when you do the core intersection argument, you get at least one correct processor, but now because N is 5F plus 1, you get 2F plus 1 correct processors in this intersection. Okay, so if none of them has voted since view V1, then the TC includes an MQC for B1 amongst its votes. And that will give us a contradiction. Otherwise, at least one of them has voted in a subsequent view, and that means they've seen an MQC for a view greater than V1. Okay, if they voted for it. So by choice of V2, this MQC must be for a descendant of B1. Okay, so that's the rough idea. We see it in a bit more detail. Okay, so first of all, by a choice of V2, the parent of B2 must be for a view less than V1. Also, B2 has to include T, which is TC for the previous view, V2 minus 1. Okay, that means then, if we look at think about this, the TC included, so the greatest MQC in any message in T and the greatest MQC amongst the votes in T, these are both for views less than V1, because the parents for a view less than V1. The correct processors are voting on this block. Now we just do our counting argument. Let P be the processors who contribute to the LQC for B1. Let P prime be the N minus F processors contributing to the TC. Okay, now, because N is greater than 5F plus 1, this is intersections of size greater than N minus 2F. And so it includes at least N minus 3F greater than 2F plus 1 correct processors. Okay. So first case, so if none of these vote in the interim views, then T contains an MQC for B1 amongst its votes. Right? That contradicts 1. Otherwise, at least one correct processor in this intersection votes in such a view, and by a choice of V2, that processor receives an MQC for a view greater than V1, right, for the parent of the block they vote on. So again, that contradicts 1. Okay, so yeah, so that gives us our consistency. And for the liveness is fairly straightforward as long as your timeouts are set correctly. So liveness is straightforward. We have processes resend MQCs and TCs upon first receipt, right? So that means that after GST, everyone's entering views within time delta of each other. So a correct leader will then follow the instructions, form a justification, and select the block specified by that justification as a parent. Okay, and then the way the instructions work here, people can vote for any block just because of the justification. Right? It doesn't matter what they've received. So correct process can then vote for the proposed block just because the parent is as specified by the justification. Okay, so then you've got to make sure your timeouts are set correctly. But again, so the calculations here are just as before. Okay, you can set your timeouts to 2 delta for the same reason that it works as 2 delta in min. Great, okay, so how long have I got? I've got like 13 minutes or so.
Yeah, about 13 minutes. Could you comment, so what would you say are the pros and cons of more the simplex style approach versus the PDF style? Is there one or the other?
Okay, so I guess there are, okay. So one disadvantage, well, yeah, we start first. So in a simplex style approach, something people object to sometimes, which I mentioned yesterday, you can have this build-up of nullifications, which suddenly, if there's a large asynchronous time period, you need everyone to get all these manage large number of nullifications. As Patrick pointed out, there are ways around that using aggregate codes and so on. Okay, so that's one sort of thing you need to consider. A potential disadvantage of the PBFT style approach, I guess the TCs, depending exactly how you do it, they may be fairly large objects. You can use threshold signatures and so on, but still you're going to have end messages in some cases. Okay, so there's now considerations there. Yeah, I guess there may be other considerations that I'm not thinking of right now, but then there's at least a couple of the trade-offs.
Well, just because there's a third option, right? That I think even at some point the tech people almost publish actually like a tendering approach.
You mentioned it.
Yeah, and then I guess connecting to kind of this complex protocol, right? So that would get really processed. Remove the long messages of PDFT, remove the long skips of syntax, and tendermint style and the latency of PDFT is something that we do. But that's the related. So that's it's complex. Combination of syntax.
And then another question, so if you actually wanted to type 5F-1 all tolerance, tweak these protocols together, that would work in different approach.
Yes, you've got to be fiddly about exactly the role of the leader and things. I'm lazy enough, I haven't.
Your intuition, is that compatible with these approaches, or is it kind of you need to do something different?
I want to be careful, I guess.
It's all, all you need to do is like just change the definition of the certificate, right? So to next year it was like n minus n votes, and now you basically have to kind of sort of like two on votes. So now you basically have to say that either that, or if there is an equation, then you don't have to just change the definition and the protocol slides. So it's a small change into what the form actually means.
Take into account.
If it, so you have a proof of equation, then you have to prove that you're voting without them. And if you just do that, then everything's there.
Okay, so just briefly then, I'll talk about a bit about erasure coding. I have to try and make this fit into time. Okay, so the idea here is at high throughputs, basically blocks are going to be much larger objects than votes. Okay, and this means the leader is going to become a bottleneck because they've got to send all these blocks out to all the other processors. So blocks of 1 megabyte, and if leader has to send 100 others, that means sending 100 megabytes of data. Okay, so a basic idea is to share the load more evenly. We could try splitting the payload of the block, right, the transactions, because they're going to make up most of the block, into sort of n fragments, if you like, into n different pieces. Yeah. And then the idea is the leader might send each processor their fragment, and everybody might echo their own fragments onto everybody else. Because that way, everyone would actually end up with everybody's fragments, okay, but it's kind of sharing the load between all the processors. Yeah? If everybody was honest, that would work. Everyone would get each other's fragments, okay? But if some processors might not echo their fragments, right, so some of the processors are faulty, Then it's going to be a little bit more tricky because we need to be able to reconstruct the payload from any subset of the fragments of sufficient size. Right? We're going to need, maybe you don't need all the fragments, but like sufficiently many of them will suffice to reconstruct the payload. So how I do that, we can do a really simple idea. So we start off with this sort of version of flight. So suppose you want to split the payload into 3 fragments so that any 2 fragments suffice for reconstruction. Okay, then we can use the fact that any 2 points on a line specify the line, right? So we can take our payload, we divide it into 2 different parts, the first part and the second part, okay? And we allow the first part to specify the value of our line at x equals 1, and that would be the fragment for P1. We allow the second part of the payload to specify the value of our line at x equals 2, and that could be the fragment for P2. At this point, we specify the line, right? So we know its value on the other positions. So here we only want 3 fragments, we could do more. So this specifies the value of the line at y equals 3, so we can just let that be the fragment for P3. Yeah. And now any 2 fragments suffice to reconstruct the payload. Right? If you've got the first 2, then you already have the payload. If you have the second and the third, then you can reconstruct the first and second and so on. Yeah? Okay. So that's all there is to it. Okay, so there we use the line, but more generally it's true. So if k points suffice to determine a polynomial of degree k minus 1, okay, so we can use exactly the same idea, right, to ensure that we can set this up so any k fragments suffice for reconstruction. We can produce any number of different fragments. Yeah. Okay, so that kind of works if the leader is honest, but then you've got a slight difficulty because a faulty leader could produce inconsistent fragments. Right? They could produce fragments looking like this, right? And then if you get these 2 or these, depends which one you'll reconstruct in different ways. Yeah? If you want to ensure that's not the case. Okay, so to solve that, we just have the leader commit to all fragments using a Merkle tree. Okay, and you have to construct this tree, but you're not going to send this tree out to everybody. Right? It's just something you construct yourself. So how do you do that? So you take P1's fragment, you take the hash of P1's fragment, hash of P2's fragment, and so on. Construct the Merkle tree, so each point in the tree is the hash of the 2 values below, and that gives you a root. Okay?
When you say you mean the leader here?
The leader's doing this, yeah. Okay, and then, as I said, we're not going to send the entire tree out, but to each individual person, we're going to send like a validation path. Okay, so what you do is, so they know this hash, so you send them the sort of sibling of each hash on the way up to here. So if for P1, we'll take this sibling, they can work out this hash, then we send them this sibling. Okay, that's like a validation path up to the root. Okay, so the fragment then is just your sort of bit of the data. A certified fragment has a bit more information. Okay, a certified fragment includes just the raw data, you're part of it. You also include the root and a validation path. Okay, so the validation path is like log n many hashes. Yeah. Okay, so what does the leader actually send to everybody then? Right, so the leader sends to each processor, well, they'll still send the block metadata, right? So the information as to which view I'm talking about, like what the parent is and so on. So that means people will immediately be able to sort of check validity as they required to previously. Right? So if you're doing a minimit style protocol, they need to say, you know, have I received a QC for the parent and nullification for the interim views and so on. So they can immediately do that. Okay, but they send them the block metadata and their certified fragment. Okay, and then on receiving the number of fragments, certified fragments, k say required for reconstruction, what processors do then, the other processors, they reconstruct the payload and then re-encode, right? They reconstruct the root. And what that means, so if the leader tries any sort of funny business, then the root won't check out. Okay, so basically what this means is that any k-certified fragment for the same root decode correctly, then any k-fragments will decode the same way. Okay.
Yep. Just a quick question about the erasure coding. So can the leader then create multiple trees? Each individual one is correct and send different trees?
Yeah, well, they can try all sorts of funny business, but basically the certified fragments include the root included in them, right? So for the same root, you can't, you know, they're not allowed to play around.
Not the same root, but I'm saying different trees with different roots and send
They can do what they
one
like.
tree to the left side of the network,
Yeah.
the other tree to the right
Yeah, yeah.
side.
But that's like sending different blocks, different people. So when you're voting, you're voting in part, no, for a particular route. Right? Okay, so if any k-certified fragments for the same route decode correctly, then any k fragments will decode the same way. Okay. So now we're going to just briefly talk about how we can sort of integrate this with Minimit. So first a bit of terminology, I'll talk about it in a rough way. So roughly the data expansion rate, that's the amount of data the leader has to send out compared to the size of a block. Okay, so without erasure coding, the data expansion rate is roughly n, because you have to send out like n blocks. Okay, so now let's see how this complies to Minimit. For some reason I've written Minimit there, I mean Minimit.
And just to make sure, what's the finality rule here? I mean, we need to have.
Well, I'll describe it for that. Okay, so it'll be like. Okay. Well, actually, I can describe finality right now. So, okay, so what we're going to do now, processes will maintain a local value, which I'm going to call blocks. Okay, and that contains all blocks B, such that they've received an MQC for B. Okay, they've also received fragments suffice to decode the payload and verify that it decodes correctly. Okay, and also we want the parents to be in blocks. And then you'll be finalized once you're in blocks and you receive an LQC as well, or if that's true for a descendant. Okay, so now the view proceeds as follows, right? So the leader sends each their certified fragment and the metadata. So that means they can, because they've got the metadata, they can immediately do the sort of checks that sort of say, hey, is the parent in blocks? Have I seen nullifications for all the interim views and so on? Okay. So each processor then checks, they check that the parent's in blocks, they receive nullifications for all interim views. And they also check the validation path, make sure that's correct. Okay, then they echo the certified fragment together with a vote, or you can make these into a single message. Okay, and then that's them doing their echoing there. And you proceed to the next view on adding a view V block to blocks. Okay, so we haven't increased the number of rounds of communication here, it's still just 2 rounds of communication. Okay, an issue here though, right? So if any processor exits the view on adding a view V block to their local value blocks, because they'll need to ensure all others can do so. Right, depending on how you think about it, maybe you need that for view progression, or if you're the next leader, you need to know that people can vote for your proposal. So first of all, we can consider like a naive approach which works, but isn't very efficient. Okay, so if I've added this block to my local value blocks, that means I've received 2f+1 votes. Okay, but you only vote upon at the same time you disseminate your certified fragment, right? So that means at least f+1 correct processors have disseminated their fragments. Okay, so one thing we could do, we could say, okay, so if we encode that f+1 fragments suffice to encode, then we're fine. Because we know I've got 2 f+1s, everyone's going to get f+1, so everyone will be able to reconstruct the block. Yeah? Okay, that's one thing you could do. It's not very efficient because now we need f+1 fragments to suffice. That's basically like a fifth of the processes. It gives us a data expansion rate of 5, which is not very good. So a better approach, which you can show is optimal, so it's optimal for 2-round finality. So to achieve a data expansion rate of 2.5, now we'll require 2 f+1 fragments to decode. Okay, on adding a view V block to blocks, that's our condition for view progression, we proceed with other instructions, right, we're not stopping, right, but we also set a timer, so running in the background. When the timer expires, we look to see how many processors, X let's say, that's the number, have sent you their certified fragments. If X is greater to 3f+1, we're fine, right? Because that means everybody's going to get 2f+1. Okay, so they'll all be able to reconstruct. Otherwise, we just send the missing number, so 3f+1 minus X processors, or other processors, their certified fragments together with the MQC. Okay, then we have to make sure they're actually going to disseminate those things, even if they've already voted. Okay, so we have an extra instruction: disseminate any received, certified fragments that have an MQC. Okay, even if you've already voted. Okay, so that suffices to ensure that everyone will be able to recover the block. Okay. And the timer here can be sort of set to taste. Basically, it should be set to roughly the time I expect to elapse between receiving 2f+1 and receiving 3f+1 fragments. So generally that could be quite small. And if you're sort of thinking through carefully, it's important that's small because this will actually increase the sort of timeouts we need in each view. But this is going to be a small increase to the timeout. So I said before, yeah, so we can prove this is optimal. Actually, data expansion rate 2.5 is best possible for 2-round finality. On the other hand, if you are happy to have an extra round of voting, 3-round finality, then you can achieve that's like a safe data expansion rate of 1.5, and you can even push the data expansion rates of arbitrarily close to 1 if sufficiently many processors act correctly. Right? If your actual number of faulty processors ends up being less than your known bound F. Okay, so there's a Cardo protocol we've written down recently which achieves that. Good, so I'll stop there. Last thing I want to point out though, so I'm writing a book, it's called A Quick Consensus, and you'll find it on my webpage. Well, it's not finished, it's like about 2/3 complete. I think what's there already should hopefully useful, so feel free to check that out. Okay, thanks, I'll stop there. Any questions?
I don't know if this is a question for you or for Roger or for both, but how would you compare your use of erasure codes with what Roger talks about with Rotor and
I am clear on my use of erasure codes and less clear on Roger's. So maybe Roger should answer that question.
Do we pass Roger?
About 2.5x being optimal. So 2.5x optimal, that's the very some part for me. I wonder why we can do it 2x.
There must be some. There must be some.
I mean, there's this trick we have with the equivocation that we need an extra proof for that. Maybe it's that part, but I don't quite see how I can do that. Oh, it's very simple.
Again, thank you for the presentation. The method tree that we wanted, it's relevant, so by the proposer through ways and data through ways there is still because they can still propose, just receiving some pieces, and even having the method tree verification, you can still receive them. So if the proposal wasn't proposed just to stop or to relocate, you cannot prevent these using method tree.
So at the moment, basically, people will sort of forward their fragment to everyone else upon first receipt. Okay, so that's like yeah, okay, fine, that will happen. And there's also some extra forwarding. You'll only do the extra forwarding if you've got an MQC, so that sort of limits the amount of extra forwarding that can take place. So there is, yeah, it's true that you can sort of force a little bit of spamming, not unbounded spamming, right? So you can force each person to send, I don't know what the number is, maybe 3 different fragments or something like that. Right?
The 2.5 you mentioned, it means that literally you have to send, so this is the number of messages you send, so it should 2.5 per month? Or this is
it's not number of messages, it's the total data, right? So you have to decide how many, is that what you're saying?
the number of bytes, so to send n bytes, you send 2.5 bytes.
Yeah.
Simplification. I'm still trying to understand the finality. So the fact that there's like 3 plus 1 that says that they're part of the work to treat correct doesn't mean they all lie on the same curve, right?
Well, if you've all got the same routes, you're voting for a particular route, right? So it could be the case that so when you do reconstruct the block, so you then check out that everything done works correctly. So
And if it doesn't?
and if it doesn't, then then you have to there's some extra instructions there. If it doesn't check out correctly, then you have to nullify it, and you actually prove that doesn't spoil consistency.
So what I'm worried about is basically that the malicious proposers are going to give all the honest parties the right curve, and then keep like one malicious party with the incorrect curve.
Or a different route.
No, not same routes. Like the Merkle is open. Well, you have to open the whole everything in the Merkle tree.
Yeah. So like when you reconstruct, when you check out, you reconstruct the truth.
One other question toward the end, you're improving the 5 to 2.5. Does that mean like data availability is going to lag consensus a little bit?
No, I mean, well, under standard conditions, right, you're still fully reconstructing the block immediately before you enter the next view. Under normal conditions, there'll be some conditions where other people have to echo fragments and so on, but you are reconstructing the block.
But like in the same 2 rounds, at the same time.
Yes, under standard conditions, yeah, that you finalise basically, well, you'll reconstruct, depending on how long the actual reconstruction takes you, but basically, yeah, imagine that's the time, no time to come. Then you'll reconstruct before you actually finalise.
Even though people have to catch people.
understand the conditions, right? But there'll be situations where there's some sort of lag because you've got the block, other people haven't, because you got some fragments from Byzantine processors that didn't send it to them. So then you have to make sure they've got them and so on. So there's some.
Because you're saying the honesty here, that gets triggered. Questions for Andy?
Thank you.